Okay, so we had the issue with the lecture date, and we will take the time from Tuesday from 4 to 6. Anyway, there will be hopefully the online recordings, and for those who are not available, so try to come. But I know for such a big group it's not really possible to everybody to come, but it's still required that you listen to the online recording and go through the slides and understand what was discussed. Of course, that's necessary. And if there's something that's concerning all, I will put up a doodle, and hopefully that should be also used by everybody. Okay, that I said. Next. Okay, so basically just the few previous slides also with regard to the input for the topics around 6. So those who need really the code to see what's working and how does it work, so that later on these people can explain to the others how it works and how to set it up and what can be done, and so this is the reason. Okay, so today we will start basically with the lecture parts, and what I will present is more on the technical background, how this P2P based social networks can be done, and we go into the details on how storage is done and what kind of technical paradigms we have at hand, what you can use. So, very early beginning, history of network services. So this was basically how the first interconnection of social networks, or whatever you call them, looked like. So very simple, and from then it evolved, so that's nothing new. Then came World Wide Web, so now we have a little bit of history basically. Some first website 1995, so very first websites came up first from companies, then more and more from private people, and it was always the need for the people to basically show what kind of people they are and to present themselves, so that's nothing new. And what was in the beginning, but what's changed basically over time, is in the beginning it was quite difficult to really do it. So you have your web servers, you have to set it up, and it was really requiring lots of technical background to be able to do it. So only large companies could do it, or universities with researchers basically. And nowadays, so that's it's also some of the first websites really, so from University of Berkeley in California and Fiat or Coca-Cola, so very early companies catching up the internet. So, but nowadays more and more you can present yourself, everybody can share his or her data, and it's really evolving in many directions, so not just one social network. This is just a few I found. So on ResearchGate I've been also once participating, so that you can connect with other researchers, but they are for any kind of subculture social network, so it's not just one big but also many small. It's, for example, a social network for prisoners, or somebody who likes to do some knitting, and so for any kind of subculture you can have a social network also for companies internally, like it was said. Okay, of course also it's difficult and problematic of what kind of data you share and who's having this data and what happens with the information that you post. So of course there's on the one side you yourself have to take care that you do not do any you do not post any data that somehow can be used against you, but also you have to trust whom you post it, so what kind of network you post it on. Okay, and there's also a trend, so that will be probably also relevant for this PG, is that you don't have them just basically on your desktop, but the mobility is also coming and catching up, so you have more and more this kind of also mobile social networks, that you can see your friends who's online, who's where, and probably some interest rate, what you can do together because of your places and your locations. So this is also coming probably, and we will see whether this will be relevant for us. Okay, so I think what is lots of text, but still what is only standing there is so many kind of social networks exist, the trend towards mobility, and we can do lots of interactions. And I don't want to go much deeper in social networks, I think everybody knows it, but the question is what is the technical background for it, so what can we do? A little bit more of social networks still. So that these are some pictures I found interesting because it just shows there's not just really Facebook. So I think Facebook's on the next one. So there's Facebook. You have Farmville, which is also very popular. So you just have lots of not just one type of social network, but many types with many functionalities that could be also combined. So if we think of the PG and what can be done, it's not just Facebook is somehow one big goal, but you can also have a look to the left, to the right, and see what other popular social networks there are. For example, of course, Skype, which focuses on audio and video streaming, Twitter for the short messages, YouTube for videos, all kind of blogs, and I mean there are various opportunities in which directions some social function can catch up. So Farmville and also the successor, it was called Cityville, that I found very interesting because there you had within 40 days from the start, so first the code and the game was available to the people. Within 42 days, 100 million users, and that's, I mean, nowhere else really reached. So that's also a nice example how these social networks can act as somehow like a platform for other applications that really are very interesting for the users. That's what I just asked. So many application types and not just Facebook, so just keep the eyes open what else can be done. Okay, just two more slides. Why is it relevant? So is it just nice for us because we use it, or is it really some commercial bigger point behind it? And of course there is. So just what is important for the social networks. So first of all, their size. So they are really reaching, I mean, almost 1 billion users worldwide, and most of the content is user generated, and all these new Web 2.0 applications focus on it to really enable users to communicate with each other, and not like previously only with one website and one provider of content. And also what was written here, Facebook traffic tops Google, so this is nowadays also the biggest traffic generator on the internet. And also looking at the websites here currently, I think it's January 2010, but nowadays Facebook's even on the number of clicks on the second place after Google. But if you look at the time, how long users stay on the website, with 7 hours a month, it's still more than anything else that is known. So very changing and revolutionary, and that's why there's a lot of opportunities. Okay, so what I want to present now is if we talk about, so we want to do it decentrally, there was this overview on how it can be done. So I want now to slowly basically introduce what is used in the P2P framework, and for that, just to give you a hint what else could be done. I think I have a yes, no, it looks just strange. So one moment, because there's some information hidden. Okay, so that's what's written. Okay, of course you can set up your own for the decentralized approaches. What is basically relevant is, of course, you could federate your web servers, you can let them interconnect, and you could also have some storage on the clients. But if you really want to go very decentralized, there are basically only two types of approaches how it can be done. So all of these basically in the upper parts of either you host it yourself with something like WordPress, or you have some web servers that you interconnect, or you have some centralized index that knows where the data of the people are, or so they need this centralized aspect, and it's not very challenging, and people still do not trust you. But if you go to really peer-to-peer based social networks, there are only two types basically. First of all, you can create a social network that takes the social topology of the people, so and puts it into a network topology. That means I'm only connected to my friends and they are only connected to their friends, and somehow we have to manage to find each other. And there I present one approach. That's SafeBook, which uses this idea and creates a social-based topology. That's the one aspect. Later on we will see the other aspect that we will use in PG, and both of them have benefits and drawbacks, but still it's good to know what's possible to do. Okay, so I think SafeBook is still called SafeBook because they are not known and nobody sued them because they sound like Facebook. So at least until they are called SafeBook, they are probably irrelevant. Okay, so how does it work? Who did it? So some people from Eurocom in France and the Darmstadt, and yeah, the main idea is to only connect to your own friends. So if you think of P2P networks like we saw the last time, so you have your own device and you want to contribute in the network, you establish these connections in the network only to your friends to create this social topology, and that's, of course, there's some sense of security because data, you trust your contacts, you trust that they do not misuse your data or something. Let's see how it works. So first of all, that's the internet. Okay. On top of it, we create a general P2P overlay. We will see what we will use this for. And then we have the social network overlay. And as you see, we have these so-called let's just think that these are your friend rings. So if this is A, then A has its ring of friends, and these friends have also some friends. So that from A's point of view, you are only connected to your friends are only connected to their friends, and so you have these matryoshkas, so to say. So this is the topology. We will see how it will be used. Okay, it's very secure. So if this is you, then you connect only to your friends, and you trust your friends, and you store your profile pictures and everything you have at their nodes. And then you create the connections, the network connections, everything is fine. This is called then your inner shell. So basically that's what's closest from the context to you. Then the next step is that your friends, of course, also have some friends, and they also have this trust relationship. This is not transitive, so you do not trust the friends of your friends, you do not connect to them, but only your friends connect to their friends. And so you have, if you apply that several times, at the end, several rings of friends, and friend of friends, and friend of friend of friends, and I think this is easy to understand, and just what you should make sure that if you do not know each other, if I doesn't know E, then they do not connect, but it's okay to have this friend in between. Okay, and so this is called matryoshka because it's this recursive friend relationship. And what you also should know is, okay, these social topologies typically require you that you store your data at your friend devices. And so, for example, in this case, I's data is stored on these 3 nodes. And now, in SafeBook, the question is, okay, I want to contact somehow, I want to look up and to get I's contacts and his profile and to see what he's doing. So I have to contact one of these nodes, but I cannot do it directly, so I have to find an entry point for the outer shell. So how do you get the entry points? So the entry points for I are K, L, and J. So them I have to find. And how do I do it? So therefore this structured overlay is used, which helps to find an inner node, find an entry point. So in this case, A is looking for the profile of B, so he starts a lookup. Basically, okay, give me an entry point for B, and this is the entry point. Now I'm happy, and now I can contact with this entry point the matryoshka of B, and in this matryoshka through several hops, so friend by friend, I come closer to the inner shell, and the inner node gives me the profile of the node B, which might be offline, and then the data goes back to A. So the goal is, like you see, you store your data on your friends' devices, you trust them, and you make sure so that's how storage is done. The finding of the data is a little bit complicated, and it's also a little bit complicated, like you see, if you have, for example, a profile picture that's quite big, it has to be transferred several times over your friends, and the only reason to do this several hops is in SafeBook the authors try to hide where your location is, so nobody should be able to attack you. They only can access you over your friends. The problem with these social topologies is typically, so if you look at these matryoshkas and it requires you to store your data on your friends, you really have to have lots of friends to make sure that your data stays online. And with this only friend-to-friend communication, your data is in this time transferred 3 times, so once, twice, and once, second, and third time. So you have additional bandwidth that is not really required. It also takes longer to find the data because you can only, as it was said, communicate with your friends. And in order to get the profile for, in this 4-shell matryoshka, for example, in average it takes 9 seconds. And that takes quite too long. So that's why these social topologies for peer-based social networks, this is one class, but we will not basically follow it because it's quite, as you see, quite slow. And for me, the reason why nobody should know and only should be able to contact me via friends is not quite obvious. So next I want to go basically, that's the summary. So social topology, everything's fine, so my data is only stored at my friends, and but it's slow. I have problems if I have only a few friends or no friends at all. Where do I store my data? And do you trust your friends in Facebook? So are they all your closest buddies? So it's also questionable. Okay, the other part that is used basically by the PG, and I want to go into detail, is basically the second type of solution, how you can do it. And this is, so ignore that upper part. The lower part is more relevant, is that you don't have one topology, one network that can only do a social network, and that requires also the social information. But what you do is to have a set of useful modules, something that can do storage, something that can do messaging, something that makes security, let's say, something that can do multicast and pub/sub, and then you have this toolbox at hand, and you can combine several applications out of it. And there's also another solution that follows this idea. It's called Pearson. I'm not presenting it, but just to know. And so in Live Social and in this P2P framework, basically this idea is followed, and that's also what we will have in the lecture. So we will see how can we do the storage, how can we find the data, how can we do multicast and publish subscribe, how is the security implemented, to just understand what do we have at hand, what kind of tools and what kind of peer-to-peer tools, so that we have basically a framework, and on top of it we can build several applications. I think that's also what this picture is just showing, because we had it, I think, two meetings ago. Just what will come in the following lectures is, first of all, today we will go more into detail on the structured peer-to-peer release. We will see what does it mean, structured peer-to-peer relay, how can we find nodes, how can we find data that we are looking for. Then we will go a little bit into replication today. And next time we will go more into the detail of secure communication and messaging primitives. That means publish, subscribe, and then multicast, and how is this done, so that you really get a feeling of how this peer-to-peer based framework works and what you can do with it. Okay, that's basically the overview for what the lecture today will go into detail in the next hour or so. And first of all, we start basically with structured peer-to-peer release. I'm not sure to whom this is a term, so who knows what the structured peer-to-peer overlay is? Please raise your hand. Okay. who, okay, you should, and okay, and so that's good, because this is really some basic that should be somehow taken by heart, so you should know at the end and of the lectures what really these aspects are and how they work, and to really take into use the concepts of peer-to-peer networking and what you can do with it. Okay, so let's start with the basic principles for structured overlays or distributed hash systems. That's basically the same. We will see what it means. That's just an overview what we will see. So that we will see what the distributed hash table is, how we get data in this distributed hash table, and we will see not these three overlays, but we will see past three. But they are all doing the same basically. Okay, so what is a structured overlay? So first of all, an overlay we had last time, that's some network that you put on top of one existing network, and that gives you additional functionality. And a structured overlay network has following properties. So first of all, the structure means that both the peers and the documents or objects have unique identifiers. So they all have a name by which you can identify them and address them. And what is characteristic? That's from the same key set. So typically your keys are from 0 to 2 to the power of 160. So you have 160 bits or 128 bits to identify your peers and your objects. And what is very important is that every peer is responsible for a range of object IDs. So if you think of these objects and the items, all of them are assigned to specific peers. So every peer has one range for which it's responsible for, and all of the objects that are in this range are managed by this single peer. So you do not search for objects, but you look for them. So it's something like routing, or if you can also think of it like an URL in your browser that you give this object ID basically, and you want to have the content from the network. So what is basically the function that these structured overlays give you? They give you the opportunity to find a peer that is responsible for a specific ID. That means to route the query and your query message towards the overlay network, to the peer which is responsible for it. There are several overlays which do it, but we will focus in this lecture basically on PAS3, which is also used in the framework. Okay, so what is the principle? To get an example, so here we have a small network with nodes A, B, and C. They are somehow connected, and now node A wants to store some data. For that, it looks for the peer, let's say in this case it's B, which is responsible for it. So we have an object, it has an object ID, and the object ID is managed by node B. So in node A says, I have this object to node B, and if somebody else, okay, this is the routing, and if somebody else is looking for the object, they also start a routing or this lookup procedure and also come to the same node, and the node B can tell, okay, I have this object and you can download it from me. So this is basically a simple idea how this distributed hash table works. And why is it good? So first of all, it's good because these overlays, these structured overlays, they allow to find content in O-log n hops. So how many hops and intermediate nodes do you need? That's logarithmic to the power of all nodes in the network. And also, in order to enable this quick lookup, every node only has to take this amount of routing table entries. So to give you an example, what does this mean, O-log n? So if you have a 160-bit node range, then the maximum number of contacts that you need to maintain is also 160. And typically with 1,000 or 10,000 nodes, you need 5 to 6 hops. So to give you some feeling. Okay, Okay, so what is basically the principle behind it of this routing? That's called distributed indexing. And indexing means basically that you have, okay, so first of all, yes, okay, they are on the same address space, so data and nodes, and the index is the information where the data is located. So basically, or where the data is stored. And all of the nodes in the network that do not have the content, they help you to find it by giving you the next better hop. So in this case, just very simple example is that there's somebody wants to look for content that's located here. In his routing table, he knows the next best hop. That's the best guess that he can do, and that node also forwards its query, and that one also forwards its query, so that you come to, at the end, to your destination node, which has the data. So it's content-based routing, and that's very nice because that you really can store documents in the network and retrieve them from the network. What is good about it? Okay, you have this ID-based addressing of items that you can store and retrieve, but you cannot search. So fuzzy queries like wildcards or I'm looking for content that contains this and that you cannot do. And what's also needed is that it's a little bit expensive, so you need to maintain the routing information. Okay. So you have to invest some traffic to keep it up, the structure of the network. Why is it? Yeah, just another motivation, and to put it in context with other approaches. So the node state is basically how much information every node has to maintain, so how many contacts it has to keep up. And if centralized, it's of course the server would have to keep everything, all the nodes connected, all the data it would require. But if one query comes, then you have it directly. And with flooding, you contact every node during the search, but no node has to maintain more than, let's say, 20 contacts. And with distributed hash table, it's quite good balance where you have all the nodes in the network used, but they do not have to maintain too many contacts and too many shortcuts in the network, but still the search and the lookup is quite quick. Okay, to go again more detailedly through it and to see how this looks like in general. So many times you have an ID space like this, for example. Just an example, typically you have, like I said, M bits, or 106 or 128 bits, and then you can think of these nodes as somehow in a one-dimensional space, and every node is responsible for a given range. For example, it's written on top of them. Yes. And for every data that you have in the network, there's also a simple rule how you find its ID. For example, some of the networks, they hash a string or hash the content of the file, and with that you get also 160 bits identifier or 128, and you have the ID of the object, and then you only have to start the lookup procedure to find the node who's responsible for it, and to upload the data to it or to download it. So, okay, so we have first step is every node should have its own ID. That's good. Next step, we have these association of object IDs to the node. So every node is also responsible for some ID range, so that the whole IDs in the network that we have are assigned to some of the nodes. So there's no ID which is somehow lost in the network. That's very important. So here again you see, okay, this is network and this is overlay, and the internet and the P2P network. So how do we then find it? again we have this routing, and what we, of course, if you would have a server, then the server would know where the data is located and which node is responsible for which object IDs, but we don't have it, so that's why we have this O-log-n steps to find it. So how is it done? First of all, very simple, like you have it in routing. You start your lookup at any kind of node in the network, that doesn't matter where you start, and with every hop you come closer to your destination node. And typically it's also that with every hop, the distance, if you for example take the minus difference as a distance, so typically, just in general, if every hop you halve the distance to your destination node, so you come closer to the destination. Yeah, and the final step is that you found the node that has the data, and that's what the routing does. And the second step is, once you know the node that has the data, you can download it from it, or you can do other things with it. There are also two approaches how to really store the data. First of all, direct storage or indirect storage. So either you could store your data directly at the node. So if you want to store, for example, a profile picture, and you have an ID for it, then you could look up the node who's responsible for that profile picture ID, and then you could upload your data to it, and everybody else who's looking for it can download it from that node. So this would be the direct storage. And the indirect storage, if you would have a very large file, then like a movie for example, then you do not want to upload the whole movie to that poor node, but you want only to tell the poor node, okay, I have the file, if somebody asks you, just send him to me and he can download it from me. So you only upload basically a reference to the responsible peer, so that if other nodes ask that reference, ask the responsible peer, they get the reference and they contact you. So it's only one hop more. Yeah, that's what I said. So it just makes that sense if the direct storage makes sense if your data is small. There's no clear rule when your data is considered small enough to be stored directly or when not, but it depends on the application. Yeah, and it's more flexible if you have it indirect, and that's not just if it's very large, but it introduces only just one single hop more, but still you are more flexible. So you could only say, I do not want to store the data myself, but I want to put it on some node with high bandwidth, or which is expected to stay very long online, for example. So you can really think about it, where to put your data. Just to keep you in mind how this structured overlay works basically, and what properties it offers. So what you should take with you, so first of all, is so up to this point of the slides, is that you have the structured overlays, that you really have peers responsible for object IDs, and you can place any kind of object with a specific object ID in the network and retrieve it. So this is the basic functionality. The last slide to this distributed hash table, so what you also have to think of is, of course, how do you put inside some new nodes and what is happening. So first of all, if a new node comes with a new ID, then it also contacts an arbitrary node, so somehow any kind of node that it knows, and makes a lookup for its own ID to see who is responsible for my current ID that I have. Once you found the node that is responsible for UID, you split up his responsibility range, and you find your position in the network, and you copy the key values of the responsibility range that you get now, and you are then placed in the network. So basically you have to find your place between all the other nodes, and you have to take your part and your share of responsibility and copy it over from the other nodes, what they have for it, and then you are basically placed in the network, and you establish your routing connections, and then you are happy. Okay, so this is basically the main idea. There are several overlays implementing it, so The most prominent one is chord, because it looks like we had it in the previous figures. Yeah, chord looks like exactly like this, like a ring with the nodes, and it's very, very simple. It's around 11 years ago when it was published, and since then several overlays came to have been published, and most frequently used in practice, at least in scientific areas, is the following one. It's called pastry, and I will introduce you to pastry and free pastry and past. So what is the difference? So first of all, pastry has also been published 2001, like most of the prominent overlays. It's a distributed hash tables. So distributed hash table means that you have this mapping from object IDs to peers, so that you really have responsible peers. And it uses prefix-based routing. So you will see how this works. And free pastry is a prototypical implementation. That means pastry is the idea, is the algorithm, it has been simulated, okay, but free pastry is a concrete implementation that is also used in the P2P framework, and that's why it's also very relevant. And there are several extensions, that means several add-ons that are also used and that will be also presented during the lectures. One of the add-ons is past, so I don't know what it stands for, but it's what it does is replication on top of free pastry. So while in pastry and free pastry you can only look up the peer who's responsible and probably send your file to him, so store your file once. If the node goes offline, the data is lost. So that's why you have past, which does the replication to make sure that if nodes go offline and they had some relevant data, the data is still available in the network. So that's what is also relevant. Okay, yeah, starting with pastry. So what is prefix routing? It doesn't help to know it's like postfix routing. So just what you should know is that if you have an identifier, and typically in pastry, it's it's 32 characters of which are hexadecimal numbers. So it means your characters are from 0 to 9 and from A to F, and these you have 32 times. And if you have these 32 characters, with every hop, at least one of your characters that you are, so if you are looking for a specific destination object ID, then with every hop, the prefix, so the first letters of this ID that you're looking for, match with those nodes that you are visiting. So with every step you come closer to your destination node, because the beginning part of the object ID and the node that you're currently at are matching more and more. We will see an example how the routing works. Just to keep and to tell you what you also have beside the routing table is a leaf set. That's something like let's see if I have an example. Yeah, a leaf set you can think of if you are a node somewhere in the network, then you would like to know your closest, numerically closest nodes, neighbors. So you want to know, if I'm that node, which are the 5 or 10 closest, numerically closest nodes. That's the leaf set. And the neighborhood set, that's more geographically close. So which nodes are also from Paderborn and also from Germany, for example. So these two sets you also have. So this is a routing table example for pastry, and what you see here is first of all lots of rows, but it's not so complicated. What you should first know, so pastry is using this 128 identifiers, 128 bits, which you can encode with different bases, so either 16 like it was said in the previous slide, or in this example it's with the base 4. So you have only characters from 0, 1, 2 or 3, and this is the leaf set. So we are currently looking at the node 102.33.102. Here's the leaf set, so you have on the one side the 4 closest nodes which are higher numerically, and the 4 closest nodes which are numerically smaller than you. These are some nodes from your same geographical location. And here you have the routing table. And if you go through the routing table, you see that basically you have for every digit and every level that you go deep, basically some entries. What you have here in the first level, like it's called, so the deeper you go, these are so your rows are levels basically, and in the first row you have the view on the first digit of the ID. So here in this case, so this is our node, and we have in the column 0 a node which differs in the first digit and starts with 0. In so in this column we have a node which has a 2 at first digit, and this has a 3 as a first digit. In the second line we have nodes which have the same prefix, so also start with 1, but are different in the second digit. So here it's the node that we are currently, the 1, 0, it's the same, but with the column 1, so the first prefix of 1 is the same, but the second digit is different. Also here the second digit is different. In the third row, the third digit is different, and in the fourth digit is different. So you see, the deeper that you get, the longer the matching prefix is, and it just differs in that specific position, and it has a number according to in which column you are. So what you have basically is just some structured representation of nodes that you know and that share the same prefix like you have. So the deeper you get, the closer numerically you come also to your own identifier, and the harder it gets to find nodes with differing node IDs. Okay, we'll see how this is used. What does this tell? The size of the leaf set. So it's twice, so if the base is B is either 4 or 16, then you have both as many bigger numbers and as many smaller numbers, and also for the neighborhood set it's just giving how many you have. Okay, so let's have an example. So in this example, it's an easier one, or at least, so I hope you is this the example? Yes. Okay. Yes? Yes?
The routing table, I don't understand the 0 and 1 and 3, these numbers which are single.
You mean, this one, so 1, 0, 3. So if you go through it, so the first row tells you, okay, so let's start different. So what you have here, what this graph tells you, is first you look, I think another slide that's probably, okay, first answer to your question, then let's see for the example. So if you go through to 102.33.102, that's your own ID. So if you get as an input, yeah, I know what to show. Let me just give you another example. I hope it doesn't crash. No, one moment, because here it is. Okay, here we have the example. So just assume we have yeah, it's basically the same routing table, the same node, base 4, and now we want to see what is the next hop in routing. So what we want to do, we get a message for the destination node K arrives at node X. So this is node X, the routing table of node X, and we want to find a better next hop. So where to send this message to. So first of all, we check if the message ID K is within our leaf set, so we are very close to it, and we know already somebody who is very close, so even more closer to it. So in this case, if K equals this number, then our neighbor here, 1023, no, that one, 10233033, is closer to K than we are, so we forward it to him. If it's not, if we are closest, or it's very far from our routing, if it's very far from our ID, then we basically look into a routing table and we check. So this is the example. So this is the incoming key, and we check, so how many digits does it match with our own ID? And this, in this case, the 103 and so on matches the first two digits with our own. So we have a matching number of 2. So that means the third digit, which is in this case, so the 2 is the first one which is not fitting, so we have to find a better one. So we look into, in this column basically it says, okay, we have a matching of 2 up to now, and now we are looking for one node which has as a next character the 3. And so we look in our table, and there it's written this node should be contacted. So we contact this node. And just why you ask, why do we have here 2? Because if somebody would require us to have 102, then we are already matching, and then the prefix is longer. So then we would anyway go deeper. Okay, so and if we have the case that we don't have any routing table entry, because for example here the matching prefix with our own is 5, so the first 5-digit match, but here we have a 1 and there a 2 is required, sorry, a 3 is required, then we see, okay, we know somebody who's still closer to that ID than we are, so that's where we forward it to. So what you basically just do, you have your routing table with some nodes that you know, and you try to have for any kind of prefix a good match. And what is basically standing there, so if you start with your own ID, so if you start with your own ID, so this is you, so this is 1, and if some other node is required, some other ID, something like 0, then you have an entry for it, you have also an entry for 2 and for 3, and this is you. And if the prefix is 1, then you have also an alternative for 0, so this is again you, but you have, if it's something else, then you have also alternative nodes where you can forward the message to. And if the prefix is 10, then you also have some next hops for the third digit, so again 0, and again something with 1 and something with 3, and this is you again. So you have just this tree structure, you go deeper and deeper for your own ID, and you have for all alternatives basically better next hop where it goes to. Okay, complicated example, but just what is the essential part is that in 3+3 what is basically, you have this prefix based routing, so with every step you come towards the destination node, destination ID at least one prefix digit more. So if you are like here for example, if you have a match of a prefix of 2, then within the next hop the next digit is also matched, and with the next hop the next digit is matched, and more digits are matched, so at the end you have all of the digits at least matched, or there's no closer one, and then you have the responsible peer found. Okay, so that's why this example is probably too simple, but it's basically also the same. So in this, what was that? I'm not sure. So here the case was routing from this node to that node, but the idea is still the same. With every digit you come, with every routing step you come one digit closer, and you just look into your routing table and see for that next digit to match which other node do I have to contact. And if you don't come closer, so because it will be not the case that you have really a full matching to all of the digits until the end, but at some point you will have no better contact and no closer node ID than your own, and then you're responsible for it. Ah, yeah, good. So here was the example. Okay, is there somehow, do you see that, do you need a further example? Should I present another one, or do you have a main understanding? I think for the next time I will present probably an easier one. Yes. Okay. What you also have, so this is how routing works, or let me just think whether it's easier to really have a simple next example. Yes, so a very simple example would be, and I would try it without, yeah, for that I need the whiteboard.
Okay, very simple example. Just think of the nodes, and now we have as a base, let's say we have only 2 digits, so base equals 2, we have only 0 and 1. And we have the node 0, 1, 1, 1, 0, 1, 1, 0. So that means in the routing table, how deep is it? So for every digit you have one entry, basically. So you have a matching, and what it tells you on the left, so in this dark blue, is basically how long your matching of the prefix is. So you start with so matching equals 0. That means you have, let's go through it. Okay. So these are the possible matchings, and oh, it's also it. So, and for all of the IDs where you are, is basically, so this is the 0 column, and this is the 1 column, and for those where you are in, so basically if the first row, let's put it like this. So here you are, this is you, this is also you, because you have the prefix 0, 1, this is the prefix 0, 1, 1, this is the prefix 0, 1, 1, 1, this is the prefix 0, 1, 1, 1, 0, 0, 1, 0, 1. 1 and 0, 1, 1, 0, 0. Okay, so as you see, with every row you get, you just extend the length of your prefix, and here you don't, this is U, so you don't have any constants there. And for all of the alternatives, you have to have one other peer. So you have to know here peer, you have to know there peer, and this one has to start with 1, this one has to start with 0, 0, this one has to start with 0, 1, 0, and so on. So you see that the beginning is always 3 digits, in this case 2 digits, this one only 1 digit, and this is U, and you always have to have an alternative. And if you extend it, so this is only with 2 digits, but if you have 4 or 16, then you have broader tables, but it's basically the same, that you just have to look around, okay, in this case I have a prefix length of 6, and for all other that is not like mine, I need alternative peers to send it very to. So that's basically what's shown here with the basis of 4, that you check how long the prefix length has to be. So this one, in this case, if it's the prefix match with the document that you're looking for, with your own ID is 4, then you need to have alternatives starting having a different 5th digit. So here you need an alternative to you, here you need an alternative to you, and there. And this is your basically place. So this is how routing basically works, and you need just a lot of contacts to quickly find your route to the peer that is responsible for the data that
Okay. So one question is, I think I go over it. Yes, so one question is, okay, so this is basically how it should look like. So if a new node joins the network, how does it fill its routing table? So how do we find, if we are very fresh node, how do we fill it? So this is done like this. So first of all, can you read it? I'm not sure. Otherwise I can explain it. So basically what you have to have, so in this case we have node Y, and it wants to join the network which has the nodes H and B and C and W. Okay, and now we have some locally closest node that we should know, and that's for example this one, because it's also from Germany, it's also from Paderborn. And then we send a join message to that node and say, hello, I would like to join, and my node ID is 6. Okay, then it performs a lookup towards to look who's responsible for the node ID 6, or the object ID 6, so who's responsible for the ID 6, and all nodes on the path answer with their own state information, so they all tell me their routing information. So if this is node Y and this is the lookup path, then all of the nodes on the path tell me how to come closer to node ID 6 hop by hop. And that's why I can take my neighborhood set, so that means the locally closest nodes, from the locally closest node I knew, so that was also from Paderborn, so I can also take his Paderborn contacts. If W, that's basically the one who was responsible for ID 6, and he all knows basically all nodes that are around node 6. So that's why we can take the leaf sets, so he all knows the IDs in the network in that area. And as we come closer hop by hop towards the node that is responsible for node 6, we take their routing table rows. That means
we were asking one node, and that was the first node. Then we take the first entry of him, and in the second hop we were going to that node, and we take his row, so we get our routing table from different nodes assembled. Okay, and at the end, so what do we have? So we have
the new node placed in its position where it should be, the leaf set is filled, the neighborhood set is filled, and the routing table is full, and then the new node checks also itself whether the routing table is valid and contacts those nodes and contacts the leaf set whether they are really numerically very close, and it updates its neighbor set. Okay, so just for how this overlay works. So something about why is it good and why is it bad. So why is it good? First of all, the nodes can go and leave the network unexpectedly, that's anyway assumed, and because the nodes periodically also check their table entries, their routing table entries, with keep alive messages, they detect, oh, the node doesn't answer in this specific column, so I don't have any entry dot there, and I drop the connection to these contact basically. So if the node doesn't answer, if it was in the leaf set, then we have to still make sure that we have the numerically closest nodes in our leaf set, so we have to find a new one. And this is basically, if you just think of the leaf set as your closest nodes in the ID space. So this is the ID space. This is your ID, and in the leaf set you have the numerically smaller nodes and the numerically bigger nodes, let's say 4, and one of them fails, then you have to get the next one, and you have to make sure that you somehow have contact to those. So typically you would ask, okay, give me your leaf set. He would give his leaf set, and then you see, this is the new one whom I can take. If it's in the routing table, somewhere here, better would be somewhere here, for example. So we have this base 4, and this node is failing, so I don't know any other nodes starting with 1, 0, and 1. So this contact is failed. So I ask some of the others, for example 1, 0, 0, just give me your routing entries, because you know more nodes in your own surrounding, and you know more nodes which have let's say a 1 there. So that's what we do. And yes, that's it to free pass to pass tree. And just so that's how the overlay basically operates. And now the question, what can it do? So what are the interfaces and how does it look like? What can we use it for? So the authors, they created a so-called common key-based routing API, which defines what pass-tree can do. And I want to go through basically these API to show you what you can use it for. So first of all, why is it a nice API for structured overlays? Because you can really exchange it, and other structured overlay also have the same API. So if you have an application and you program something towards this API, then you can have pass-tree implementing it, you can have other overlays implementing it, and then you can exchange basically the overlay and the DHT that is used. Just what you should know, because it's a C notation, so if there's only one file, that means in the interface that you can only read it. If it's two arrows, then it means you do not only can read it, but you can also write it to it for the results. So what can you do? So first of all, you can route a message. Here's the message to a specific key, and you can give a hint. That means what is the next hop. As it was said, for routing you can start with an arbitrary node for your lookup, but if you give the hint, then you start with this node as a first hop in your lookup, basically. And here you give the node handle, it's something like IP address and port. So So this is how you can route. What is also happening, so just also draw it, that's probably nicer, because then it's easier to understand. Yes. So like it was said, in routing you have this, if this is the IDs range, then you have this multiple hops. This is your destination key, this is your hint, so your first hop. I mean, you could have also started something like this, but you want to say first, use this as first hop, and now you have this forward function. That means that every time, so if this is a node, and every time somebody uses you as a next hop, the application, which is somehow connected to it, is informed about what is the current key that is looked for, what's the current message, and what is the next hop. So that the application can either say the next hop should be something else, or it can use it for some whatever. So you just have insight into the messages that are passing by. Okay, and if you are the last hop, so this is the final destination of the message that was directed to this key, and you are responsible for that key, then the message, the function deliver is called, deliver, and your application gets the message. So that's basically the last function. Okay. This was the first part, and this is basically the second slide to it, what it can also do. What you also have is that you can ask your local state, basically. So if you make a local lookup, then and ask, give me for that specific key that amount of contacts that I can use as a next hop. That means that you would get as an answer a list of node handles, that means IP addresses and ports of nodes that you can use as a next hop. That's part of the API. And what you also have is, if you want to have a neighbor set, so give me so many peers from my neighborhood list, that means from my contacts. That's, for example, if you want to use some nodes to contact and to choose them randomly, for example, then you can pick with this method some of them. What's very useful is this replica set. So that means it returns an ordered set of peers of magnitude on which an object with key with the given key can be stored. So here say how many you want to have, and here you tell for which ID. And that means if you are some node, and this is this is you, and this is your responsibility range, let's say, and this is some object K, then you want to ask, give me potential other nodes, for example here and there, and I want to have 4 of them on which I can store K. So for example, I store them here. And the good thing is that this is not really related to this peer, but if some other peer also, for example here, asks, give me the replica set for of the node K, then he would also get the same context. So everybody can check who are the replicas for that given key. That's quite useful if you want to do some replication. Okay, what you also have is the update and the update message. That's basically, if again this is the ID space, and this is you, and these are your known neighbors, and some new node appears, then you are updated and you get the information, oh, somebody new appeared. And if somebody leaves the network, then you are also updated, oh, somebody left the network, so that you can use it for your own maintaining of routing tables. And the last one is basically that you want to know, yes, for this node handle, what is the responsibility range? So what is the responsibility range for this node, for example, so that you know, okay, I'm responsible for this area, and that's also good to know. So with these, I think these are eight methods and functions. This is basically what all of the structured overlays that are typically discussed can do, and this is very useful because you only have these at hand to build more complex things, and this is quite useful also to keep in mind, so what you can do and what you cannot do. So you cannot do magic. You cannot do magic. You can only use these functions to create replication, to create multicast, to create whatever you want to do. Okay, so far to Pastry and what API it provides. Now FreePastry, and FreePastry is, that's why important and relevant, because it's also